Hi there, once again welcome to the Logic of Risk. In this episode we continue our discourse about probability. Last week we said that a probability is a real number between 0 and 1 which we use to quantify the randomness of an event. A probability of 0 indicates that something is not possible, while 1 indicates almost certainty, or, if you prefer, certainty in practice. We also mentioned a few other points, and I just refer you to the last episode in case you missed it. We know that if an event has a given probability, say 20%, its negation, which we formally call the complement of that event, has a probability of 80%. In decimal form, that's 0.2 and 0.8. Okay, let's start from here. If I flip a coin, which we will assume is fair for now, there is a 50% chance I will get heads, and a 50% chance I will get tails. If the probability of heads is 0.5, then the probability of tails, its complement, is also 1 minus 0.5 equal to 0.5, and together they sum to 1. If I asked what's the probability of getting heads or tails from flipping the coin, you would say 1, because one or the other will happen. The probability that an event or its complement happens is always 1. However, even that coin flip example isn't entirely correct, because in reality a coin might land on its edge, leading to a third possible outcome: neither heads nor tails. In an ideal game, we might decide to rule that out as impossible, but in real life it isn't. Someone might say that event is practically impossible. Let's just call it impossible. And I might even agree. But let's wait until we talk about effective nullity or effective zerohood. What happens if our model says the event is impossible, yet it actually happens? Do we yell black swan or curse bad luck or blame the evil eye? If we don't anticipate anything terribly negative from a coin landing on its edge, ignoring it might be okay. But if the consequence, though remote, is devastating, we should think twice. This, by the way, is exactly what certain financial wizard did with the possibility of major banks defaulting during the 2007-2008 financial crisis, and we all saw how that turned out. In general, we should never, and I repeat, never, consider any event completely impossible or completely certain, unless we are talking about special cases, usually purely logical in nature, following what is known as Cromwell's rule. We will come back to that later on. Studying probability theory means trying to answer slippery questions, and those answers often lead to even more slippery questions, though they do get more and more fascinating as we go. A fundamental part of defined probability is analyzing the concept of an event, the object to which we assign probability. An event can be simple or composite. Consider a standard six-sided die. We assume that if we roll it, it can only land on one of its faces. No crazy balancing acts for the moment. If I roll the die once, the possible outcomes are 1, 2, 3, 4, 5, or 6. So there are 6 possible results. If I gather these results in an ensemble, imagine physically putting the numbers 1 through 6 into a little bag, I get what we call the sample space in probability theory. The sample space is just the set of all possible outcomes from a random phenomenon. In the case of a die, enumerating them is easy. In even slightly more complex scenarios, enumerating them becomes a lot less straightforward, though still usually doable. An event may correspond to one specific outcome, which we call a simple or elementary event. For example, rolling the die once and getting exactly 3 is a simple event. But we can also have composite events that group multiple outcomes. For instance, I might be interested in the probability of rolling an even number. In that case, the event manifests itself if I roll a 2, a 4, or a 6. That means I'm merging multiple outcomes into one single event. Returning to the simple event of rolling a 3, I can also implicitly define its complement, namely rolling anything but 3. That complement is a composite event consisting of rolling a 1, 2, 4, 5, or 6. Among all the events we can imagine, one is called the certain event. And yes, it's essentially the entire sample space. If my event is any of the 6 sides of the die comes up, it obviously has probability 1, because rolling the die once will definitely yield one of the numbers 1 through 6. Another important event, the empty or impossible event, is the opposite of the entire sample space. Mathematically, it is represented by the empty set, the set that contains nothing, not even itself, and its probability is always 0. Stretching the concept slightly, we could assign the empty set to all those outcomes that really can't happen, like rolling a 7 on a single 6-sided die or rolling nothing at all. Another step forward. Alongside the sample space, we define the event space, which is the set of all the events a random phenomenon can generate. That is, the set of all possible single outcomes and all possible combinations of those outcomes. So it is the set of every simple and composite event. Of course, the event space depends on the phenomenon we are considering. The event rolling a 1 and rolling a 2 is impossible if I roll the die only once, but with 2 rolls or 2 dice simultaneously, that event becomes possible. When we get to the axiomatic definition of probability, we will formalize these concepts a bit more, without going overboard, but for now, that's enough. If any of you already know all these, I apologize for the many simplifications and approximations. They serve the purpose of helping everyone follow along. This is meant to be an exoteric, not esoteric podcast, open and accessible to anyone interested and not just a restricted club for initiates. Two events are called mutually exclusive if they cannot happen simultaneously. If a box contains a red and a blue ball and I draw one blindly, I will end up with either the red or the blue, but not both at once. In the die example, if I get one face out of 6, I can't get a different face at the same time. Similarly, getting a number lower than 2 and getting a number greater than 4 exclude each other in a single row. If two events are mutually exclusive, the probability that either event happens, the probability of their union, we would say, is simply the sum of the probabilities of the individual events. Conversely, the probability that both happen together is necessarily 0. But many events are not mutually exclusive, and in that case we have to pay attention to what happens if they happen at the same time. I might want to look at the probability of rolling a number less than 3 while also being odd. These events can definitely happen together, rolling a 1, for instance, so we are interested in their intersection. Two events are called independent if the probability of one does not depend on whether the other has happened. Otherwise, they are dependent. Working with dependent events is substantially more complicated than working with independent ones. All of these sets the stage for introducing a first definition of probability, the so-called classical definition. As mentioned, and as we will soon see, it is mainly of pedagogical value, barely useful outside certain well-defined theoretical gambling scenarios. The classical definition of probability has its roots in Bernoulli and Laplace, and even earlier in the Renaissance work of Pacioli and Cardano, later taken up by Pascal and Fermat. According to this definition, the probability of an event is the ratio of the number of favorable outcomes, those that satisfy the event condition without implying any sort of positive or negative judgment, to the total number of possible outcomes, assuming they are all equally likely. Clearly, we have to be able to count all those outcomes in the first place. One early puzzle that brought this counting outcomes approach into the limelight was posed by the Chevalier de Marais, a 17th century nobleman and enthusiastic gambler. He was stumped by wagers that seemed straightforward, but consistently lost him money. Specifically, he asked Blaise Pascal, which is the more likely, rolling at least one 6 in 4 throws of a single die, or rolling a double 6 in 24 throws of 2 dice? The Chevalier assumed the two events would be equally likely. However, by systematically enumerating all possible outcomes and comparing them to the total, Pascal showed that an intuitive guess can be misleading in probability. He discussed the results with Pierre de Fermat, making some moderate fun of the arguments of the Chevalier de Marais. If you are curious, the event of rolling a double 6 in 24 throws of 2 dice is slightly less likely. This puzzle, and others like it, help cement the idea of the classical definition, where each outcome is presumed to be just as likely as any other. The classical definition is indeed linked to the principle of indifference, which says that in the absence of strong evidence to the contrary, we should not consider some outcomes more likely than others. But is that always the right move? If I roll a standard six-sided die, it's easy to assume each face 1, 2, 3, 4, 5, 6 has an equal chance, and that's usually correct for a fair die. If I consider a single roll of such a fair die, the probability of any one face is obviously 1 over 6, about 17%. I have one favorable outcome out of 6 possibilities, each presumably equally likely. But what if the die is chipped, or we suspect it is loaded? Then the principle of indifference doesn't hold as strongly. Anytime we can't be confident that all outcomes are symmetric in probability, we need different tools or additional information. That's one reason the classical definition, while elegant, doesn't always match the complexities of real life. Moreover, in discrete scenarios like dice, counting outcomes is relatively straightforward, but as soon as we move to continuous sample spaces, like choosing a random real number between 0 and 1, what does it mean for each number to be equally likely? That question leads to intriguing paradoxes, such as Bertrand's paradox, that dramatically illustrates how a naive application of equally likely outcomes can fail in continuous probability. In 1889, Joseph Bertrand asked what the probability is that a random chord in a circle exceeds the side length of the inscribed equilateral triangle. Depending on how one defines random chord, the answer varies, even though each of the three methods Bertrand proposed claims to use equal likelihood. This discrepancy contradicts the principle of indifference when applied blindly to geometric situations. Later, the excellent Edwin T. James resolved the paradox by advocating the principle of maximum ignorance. Instead of assuming that all outcomes are equally likely in a simplistic way, we adopt the least biased distribution consistent with the information we have. This approach restores consistency and highlights the importance of being precise about what random truly means in any probability problem. We will return to this topic soon. There are many other reasons to criticize the classical definition of probability and demonstrate why it is unfit for real-world applications, but we will address those in the next episodes. Next week, we will introduce the frequentist definition of probability developed by von Mises and others, along with some interesting, at least I hope, practical reflections. We will challenge the classical definition by presenting an alternative perspective, marking the beginning of our exploration of the different schools of thought on probability. So, I hope to speak to you soon and I wish you all the best. Ciao ciao!